Supposedly we should have 26 students. Okay, now we have around 20 students. Okay, we can start now. Okay, guys. Just give me a second. Okay. Sorry. Okay, we shall start now. Okay, guys, this is your first tutorial. Now, this tutorial covers lecture 1 and lecture 2. Okay, this tutorial covers lecture 1 and lecture 2. Usually for previously when there's no MCO and I'll be having a face-to-face lecture time, I will have my tutorial, and what I'll do is I'll ask you to do the tutorial for 5 minutes for each question, and then once you have done, I will start giving the answer or discuss the answer with you on the whiteboard inside the classroom, so it is more interactive, right? Tutorial needs to be interactive. But since this is all virtual class, so I'm trying to figure out what's the best approach for me to teach you tutorial, which it should be interactive, but there are some challenges associated with it. I'll try my best to make sure that you understand all the tutorial questions. Okay, now guys, I want it to be interactive. All of you have opened tutorial 1, right? Okay, we can have a chat box here. All of you have opened the tutorial 1. If you haven't done so, please open up your tutorial 1. Okay, can you hear me? Okay, all right, good. All right. Now, if you look at tutorial 1, the first question, explain solid solutions. And the second one, first question, part B, describes substitutional solid solution and interstitial solid solution. And part C, based on the Hammurabi rule, provide 4 conditions of substitutional solid solution. Now this tutorial first question associated with lecture 1. Now I'm giving you 5 minutes. Okay, I'm giving you 5 minutes. Try to digest the question and try to find the answer. Okay, let's do it this way. I'll give you 5 minutes or less. Try to digest the question and try to understand the question. Then I will give you the answer. Then we can discuss from it. Okay, I will give you the answer later. From there, we can discuss and take up from it. Okay, guys, I hope that you're trying question 1, explain solid solution. Okay, let's look at the answer. Let's look at the answer. Okay, can you look at the answer? Microsoft Office, Word. Can you see the answer? All right, now, okay, question 1, it says that explain solid solution. Okay, a solid solution is the solid state solution of one or more solute in a solvent. Okay, so it means that in a solid solution, the keyword here, guys, okay, the keyword here, guys, the solvent remains unchanged by addition of solvents. Okay, this is the keyword. All right, so, and also when the mixture remains in a single homogeneous phase, that is what we call as a solid solution. Okay, I'm repeating again, for solid solution, the answer, the keyword for the answer is the solvent remains unchanged by the addition of solutes. So when you are adding some impurities on the solvent remains unchanged. You are just adding 2 different types of material in a solution, and those 2 different types doesn't replace or diffuse into it. Okay, there is no chemical reaction into it. Whereas for substitutional solid solution is when the keyword here is when the solute atoms of the element replace those of the solvents in the crystal like this. Okay, please take note of these, guys. Okay, for substitutional solid solution, the keyword here is when the solute atom of the element replace those of the solvent atom in the crystal lattice. Okay, now and also for interstitial solid solution, the keyword here are Solute atoms of the elements are positioned in the interstitial spaces between solvent atoms of the crystal lattice. Okay, so to recap for question number 1, a solid solution, solvent remain unchanged. Substitution solution, solute of the elements replace those of solvents atom in the crystal lattice. Interstitial solid solution, solute atom of the elements are positioned in the interstitial space between the solvent atom of the crystal lattice. Okay, these are the keywords that you need to have when you're answering a question involving the explanation of solid solution and the explanation of substitutional solid solution and interstitial solid solution. Okay. Now, question 1C, based on the Hammurabi rule, provide 4 conditions of substitutional solid solution. So if you look at the slide show, lecture 1, let me see that. Lecture 1, slide number 11. Okay, condition for substitutional solution. The first condition is atomic size factor. The second condition is crystal structure. The third condition is electronegativity. And the fourth condition is valence. Okay. The question says, provide 4 conditions of substitutional solid solution. It just provides 4 solutions, that's all. If let's say the tutorial question asks, describe 4 conditions for substitutional solid solution, then you need to describe each of the factors. For example, the description for atomic size factor, how big, what is the relation of atomic size factor to the, what they call that, impurities. What is the relation of crystal structure on the, what they call that, substitutional solid solutions. What is the influence of electronegativity? Does electronegativity needs to be higher or lower for substitutional solid solution or imperfections? And what is the meaning of valence? And what is the value of valence for the influence of substitutional solid solutions? Let's say if the question asks you to describe, you describe. If the question asks you to list, you just list it out. Okay, so just a quick recap. For question number 1, you just need to explain what is solid solution, what is substitutional solid solution, what is interstitial solid solution, and also the 4 conditions of substitutional solid solution. Okay. All right, let's look at question number 2. Okay. List 3 types of interfacial defects. Describe the structural gain boundaries. So we need to describe something. Okay, list 3 types of interfacial defects and then describe the structural grain boundaries. Now, for the answers, I won't be uploading the answer. You can take a screenshot and you need to do the tutorial. All right, guys, Lim Weng King asked me whether I will upload the answer. I won't upload the answer. Okay, you need to do the tutorial. Try to do the tutorial. That's where you practice yourself. All right. And then if you have question, you can ask me offline. It's better. I mean, you know why? The reason is when I upload the answer, human psychology, okay, students tend to make use of the answers. So I don't want that. You try to do the question and improve yourself. And if you have question, learn on the hard way, and then I'll explain to you further. So by that, you can learn a lot of things. Trust me. Okay. Okay, guys. For question number 2. All right, list 3 types of interfacial defects. Describe the structure of grain boundaries. Okay, try to look on the notes and let's see the answer. You want to take screenshot, it's up to you, but if possible, don't take screenshot. Try to answer by yourself first so that you can learn something on tutorial. Okay, so I'm sharing my screen. Advisable not to take screenshot, but if you want to take, go ahead, no problem. But try to learn. Okay, if you want to take screenshot, okay, it's okay. Save it and don't look at it first. Try to answer the tutorial, then you can learn better. Okay, let's look at the answer. List 3 types of interfacial defects. The first defects is external surface, and then you have grain boundaries, and then you have twin boundaries. Okay, you have just listed and describe the structure of grain boundaries. Okay, for grain boundaries, surface imperfection that separates grain from different orientation. This is the keywords that I need. Surface imperfection that separate grain of different orientation. This is the keyword. If I have this keyword in your test or exam, you will have your marks. And then you can explain further for you to get extra marks. The grain boundary, a narrow region between two grains, which is approximately 2 to 5 atomic diameters width and contain mismatch atom from adjacent grain. This mismatch atom from adjacent grain is from different orientations. Okay, these are the keywords. Okay, this is the keywords. Right? Okay, question number 3. Okay, look at question number 3. Provide 2 types of diffusion. Okay, this is associated with lecture 2. Provide 2 types of diffusion and 2 mechanism of diffusion. 3B, explain the differences between self-diffusion and interdiffusion. So you need to explain. 3C, state 2 reasons why interstitial diffusion is normally more rapid than vacancy diffusion, which I've discussed today, earlier in the lesson, interstitial diffusion. And then 3C, do you agree or disagree with the following statement? Explain your answer. Okay, this is the test of your knowledge. Diffusion occurs more readily in coarse grain structure than in fine grain structure. Do you agree with this? Okay, you can see this in the factors that influence diffusion over here, all right? Higher temperature facilitate higher diffusivities. Is it correct? Do you agree with this? And also diffusion declines rapidly along the grain boundary. Is it correct or wrong? Do you agree with this or wrong? Okay, try to digest the question. 5 minutes. Then I'll show you the model answer in less than 5 minutes. Okay, let's look at the answer. Okay, guys, this is the answer. The question asks, provide 2 types of diffusion and 2 mechanism of diffusion. That's all. So types of diffusion, self-diffusion and impurities diffusion, which is interdiffusion. Mechanism of diffusion, there are 2 types, vacancy diffusion and interstitial diffusion. Straight bullseye, okay? Straightforward. Now the next question 3b asks you to explain the difference between self-diffusion and interdiffusion. So you need to explain. Okay, self-diffusion is atoms exchanging position that are of same type. Okay, based on the lecture notes. Interdiffusion, diffusion of atom of one metal into another. Okay, impurities, interdiffusion. Self-diffusion, same material. Interdiffusion, two different types of material. Okay. Now 3c, state two reasons why interstitial diffusion is normally more rapid than vacancy diffusion. All right, the answer is first, interstitial atoms are generally in smaller size. So this is the keyword. For interstitial atom, the size are smaller. So when the size are smaller, I did remember I quoted an example of a traffic light. Okay, you are driving a car. There's a traffic jam. Motorbike can seeps in through the traffic and it goes further in front. So exactly the same thing is happening here. For interstitial diffusion, which happens more rapidly or more faster than vacancy diffusion because interstitial atoms are smaller in size. So when the size is smaller, the mobility of the atoms are faster. And also, there are much more interstitial space as compared to vacancies. Interstitial space in terms of voids, V-O-I-D-S, voids. So these are the keywords. The keywords are smaller in size, mobility of atoms are faster, more interstitial space. Three keywords. Then you can just write it down to explain the keywords. Okay. Now next, D. Do you agree or disagree with the following statement? Explain your answers why. All right. Now the first statement, diffusion occurs more readily in coarse grain structure than in fine grain structure. Okay. So the answer is no, you can't agree with that. Okay, because diffusion occurs more readily in fine grain than coarse grain. Okay, because diffusion occurs, highlight this, more readily in fine grain than in coarse grain metals. Okay. Grain boundaries impede. Okay, grain boundaries stops orderly atom movement. You agree on that, right? That's the basics of grain boundaries. Okay, when you have a grain boundary, it's a boundary, for example, between two different atoms having a different plane or orientation. So when there is a grain boundary, it impedes or it stops or slows down the atom movement between adjacent atom and help random movements. Okay, atomic disorder at grain boundaries is more than within the crystal and less hindrance by adjacent atom due to less lower bonding atom. These are explanation for it, and therefore diffusion occurs more readily in fine grain than in coarse metal. Okay, next, higher temperature facilitates high diffusivity. So do you agree on this? Absolutely yes. Okay, the atoms have higher thermal energies and therefore greater probability of being activated over the energy barrier between atoms. So the keyword is higher thermal energy and greater probability of being activated. Okay, next statement. Diffusion declines rapidly along the grain boundaries. Do you agree with this? No, disagree. That's the reason is along the grain boundaries, this is a zero zone, this is a zone of crystal imperfection and of low packing. So if you have crystal imperfection along the grain boundaries, atom can move further. Okay, random movements because you have lots of voids. So when there is lots of voids, you can go for this interstitial diffusion. Okay. All right. Now, next question. Okay, now we are into calculation. Now, for calculation, let's try this. Calculate the equilibrium number of vacancies per cubic meter for copper at 850 degrees Celsius. Okay, so your temperature is 850 degrees Celsius. The energy for vacancy formation is 0.9 eV over atom. The atomic weight and density at 850 degrees, atomic weight is 63.5 gram per mole, and the density is 8.4 gram per centimeter cube. So you need to calculate the equilibrium number of vacancies per cubic meter. So in lecture 1, this is the formula that you need to use. Number of vacancies per meter cube. Okay, try this now. While trying, I'll show you the answer. So this is the answer. So NV is number of vacancies per meter cube, NV, number of vacancies per meter cube, and N is equals to total number of atomic sites, exponential. Your Q is energy required for the formation of vacancy, and then K is your Boltzmann constant, T is your absolute temperature. Now, based on the question, you need to find the N first. Okay, for you to find N, they have given you the atomic weight and also the density. So for you to find the total number of atomic sites is Na. Okay, Na is your Avogadro's what they call number, 6.02 times 10 to the power of 23. Okay, over mole times with your density of your copper. Change that unit into meter cube, from centimeter cube to meter cube, divided by your atomic number of copper, which is 63.5. Then you have the number of atoms, sites per meter cube. So that is your N. Okay. So once you find the N, you need to find the number of vacancies at 850 degrees Celsius. So convert this to Kelvin, which is this 1123. So N is 8 times 10 to the power of 28 meter cube. Exponential of bracket negative Q is your energy for vacancy formation, divided by your Boltzmann constant, 8.62 times 10 to the power of negative 5, which is given in the lecture notes, times with the temperature, absolute temperature. Then you have your answer. Okay. You can take a screenshot of this and try this. Okay, now let's look at the next question. Question number 5. All right, a sheet of steel of 2.5 mm thick, okay, 2.5 mm thick, has a nitrogen atmosphere on both sides at 900 degrees Celsius. Okay, and is permitted to achieve a steady state diffusion condition. Okay. The diffusion coefficient for nitrogen in steel at this temperature is this 1.2 times 10 to the power of negative 10. And the diffusion flux is to be found to be 1 times 10 to the power of negative 7 kilogram per meter square second. Also, it is known that the concentration of nitrogen in the steel at the high pressure surface is 2 kilogram per meter cube. So this is high pressure surface. At the surface, okay, CS. How far into the sheet from this high pressure side will the concentration be in 0.5 kilogram per meter cube? So your CO is 0.5. So they ask you what is the value of X. Okay, CS is 2, CO is 0.5. So what is the value of X? Okay, try to look at the formula. Here, CACB minus XB. So you need to find the value of XB. Okay, now let's look at the answer. So this is the formula that I need to use. Diffusion flux J. They have given you the diffusion flux, which is 1 times 10 to the power of negative 7. And the diffusion coefficient, which is D, is 1.2 times 10 to the power of negative 10. Okay, D and J. Okay, CA is 2. It is on the surface. CB, it is on the far side. We don't know what is the distance, which is 0.5. XA, which is at the surface, is 0. Okay, if you look at the notes, okay, let me show you the notes. Where is it? Okay, yeah, here. Okay, XA is here. Okay, X is 0, so it is CS. All right. So that's the reason why it starts with 0 at the surface. So put all the informations into the formula for diffusion flux, and then you find for XB. Then you have your answer 1.8 times 10 to the power of negative 3. Try this now, guys. Try this now. Okay, it is highly advisable, without looking at the answer first, try to do it by yourself. Sharpen your skills, then look at the answer. Then you can learn something. Okay, let's take a break for 5 minutes. Try to do it, try to understand, and if you have answer, please ask me. Okay, let's take a break for 5 minutes. Okay, guys. All right. Hope all of you have tried your tutorial. It's just so simple. Okay. I'm just repeating the advice again. All right. For this subject, all the questions are straightforward. The calculation questions are straightforward. All right. There will be more testing on your theory understanding because all the assessment will be done here. So I'll be testing more on your theory, what they call that understanding. Okay. All right, now let's look at the next question. Okay. Now, one certain cube ion of 2 mm thick was exposed to carburizing gas at a temperature, so carburizing atmosphere on one side and decarburization. Hello, can you hear me? Guys, can you hear me? Okay, because I'm all right, clear, right? Because I'm having a pop-up message saying that a bad internet connection. Okay, then. All right, let's do it again. Okay, a sheet of BCC iron with 2 mm thick was exposed to a carburizing gas atmosphere on one side and decarburizing atmosphere on the other side at 675 degrees Celsius. After having reached to a steady state, the iron was quickly cooled to room temperature. Okay. The carbon concentration at two surfaces of the sheet were determined to be 0.015 and 0.0068 word percentage. Okay, guys, remember on the lecture just now, there's one student asking me on the concentration, do we need to use kilogram per meter cube? So yes, okay, for this question, you need to convert this concentration into kilogram per meter cube, and then you need to compute the diffusion coefficient given diffusion flux as 7.36 times 10 to the power of -9. So your J, diffusion flux J is 7.36 times 10 to the power of -9, and convert the concentration of both to kilogram per meter cube. And you need to find the diffusion coefficient. Try now guys, while I give you the answer. Here you go. All right, the question asks you to compute the diffusion coefficient at the given values. Now, you need to convert the carbon concentration to kilogram per meter cube. Okay, let's convert the carbon concentration of 0.015 weight percentage of carbon to kilogram per meter cube. So in order to convert, you need to know the density for carbon and density for, this is density for carbon, which is 2.25, density for iron, which is 7.87 gram per meter cube, gram per centimeter cube, sorry, that's why you times it 1000. So convert it to kilogram per meter cube, and for the concentration of 0.0068 weight percentage of carbon, you convert it into kilogram per meter cube using the density of carbon as 2.25 and density of iron of 7.87. You have the concentration in the units of kilogram per meter cube. and then use the formula. D is equals to minus J bracket XA minus XB over CA minus CB. So D is your what they call that, your main function, right? You want to find D. Put in the formula and you got your answer over here. Okay. Try now. If you want to take a screenshot, you may take the screenshot now. Okay, now let's look at the other question. Okay, the next question. Diffusion coefficient for iron in nickel are given at two temperatures in the table below. So you have temperature T into Kelvin 1473 and 1673, and this is the diffusion coefficient. All right, 2.2 times 10 to the power of negative 15 and 4.8 times 10 to the power of negative 14. Okay, find the value of diffusion coefficient D naught and the activation energy QD, and also the magnitude of diffusion at 1300 degrees Celsius. For this question, you need to use this formula, diffusion coefficient, where D naught is a temperature independent pre-exponential diffusion coefficient D naught, and D is the diffusion coefficient at a given temperature, and exponential of QD is the activation energy, R is the gas constant. You can take the value of gas constant, look at your lecture slides, and T is absolute temperature. Okay, use this formula to answer for this question. So they have given you D, diffusion coefficient. You need to find of the diffusion D naught, which is independent of temperature, and the activation energy QD, and the magnitude of D at 1300 degrees Celsius. Okay, let's look at the answer. All right, this is the answer. So at first you need to determine the value of D, right? So to determine the value of D, you need to cancel off the exponential. So to convert the exponential, you need to introduce ln. Okay, ln in both side of equation. So this is the value, ln D1 is equivalent to ln D naught, okay, minus QD over RT. Okay, minus QD over RT, the same thing, huh? Okay, I'm just cancelling off the exponential, introducing ln D1, which is diffusion coefficient dependent of temperature, is equals to ln D naught. D naught is independent of temperature, minus Q over RT. For D2, the same formula, introducing ln for both sides of the equation, ln D2 is equals to ln D0 minus QD over R T2. So given on the table above, T1 is equals to 1473, T2 is equals to 1673, and D1 is equals to 2.2 times 10 to the power of negative 15. D2 is 4.8 times 10 to the power of negative 14. Putting this value into QD, okay, you want to find QD is equivalent to minus R, okay, simultaneous equation minus R ln D1 minus ln D2 divided by 1 minus T1 minus 1 over T2. So this is your R, gas constant. So gas constant, you have two options. You are using J mole per Kelvin based on the formula, based on the units, times with ln D1 is 2.2 times 10 to the power of negative 15 minus ln D2, which is 4.8 times 10 to the power of negative 14, divided by 1 over T1 minus 1 over T2. Then you find the QD, which is the activation energy, or the energy required to produce diffusive motion in 1 mole of an atom. QD is the activation energy. So the answer is 315650 joule per mole. Okay, the question also asks you to find the value of D0. Okay, so for D0, based on the formula, D0 is equals to D1 exponential of QD over RT1. All right, so for this, D1 diffusion coefficient is 2.2 times 10 to the power of negative 15. Exponential of QD, your QD value, that is, you have find out, okay, 315650 joule per mole, divided by R1 is your gas constant times with T1, which is 1473. Okay, so the value of D0 independent of temperature is 3.5 times 10 to the power of negative 4. Okay, try now, guys. If you want to take a screenshot, you can take now and you can try it out. Okay, try now. Okay. Now next question. What is the magnitude of D at 1300 degrees Celsius? Now you find your D0, which is independent of temperature. So the magnitude of D at 1300 degrees Celsius. So D is equals to D0 exponential QD over R T1. So your T1 is 1573. So it is 1573 over here. Your gas constant. Your QD activation energy is this, as you find out over here, exponential D0 over here and you have the answer 1.1 times 10 to the power of negative 14 meter cube per second. Okay. All right. Please take a screenshot. I want to move my screen. Okay, just a quick recap. For question 7, diffusion coefficient for nickel and iron are given in two temperatures in the table below. Okay. Determine the value of D naught and activation energy. You need to find the D naught and activation energy. So for you to find D naught, cancel off the exponential, introduce ln, and you can find D naught. Sorry, you can find D naught over here. You want to find the Q, okay, activation energy, QD. Introduce ln, find the Q, activation energy, and then find the D naught, which is diffusion coefficient independent of temperature, and then find the magnitude of the diffusion coefficient dependent of temperature at 1573, and you have the answer here. Okay. All right, guys, let's move on. Let's move on to the next question. Okay, now, all right, for question number 8 and question number 9, we haven't started the lecture yet. Okay, I'll be starting this lecture next week onwards, but since it is in the tutorial question, I just leave it. I don't want to delete this, just leave it. You can try it out if you know how to solve this, or else we can take it up to our next tutorial. Right, calculate the number of aluminum atom per centimeter cube given that the lattice parameter of FCC aluminum is 0.405. And also for question number 9, calculate the theoretical density of BCC, body centered cubic iron, given that the lattice parameter of iron is 2.866 times 10 to the power of negative 8 centimeter, and the atomic weight of iron is 55.847 gram per mole. Okay, this topic I haven't teach you yet, but it is in the tutorial question. You want to try, you can try, or else I'll take it up to next tutorial. We can discuss on this once I've teach the lecture. Okay, it's pretty simple. It's pretty simple. Don't worry about it. Okay, guys, any questions? Any questions, guys? We are coming towards the end of the tutorial lesson. Are you there? Can you hear me? All right. So just the tips, guys, just the tips, because we don't have any face-to-face lecture. For this tutorial question, I've given you the solutions. So you can take the screenshot of the solutions. And by not looking at the solution, try to answer the question first by referring to your lecture notes. Then you can look at the question as a reference. All right, as a reference. I will upload the answer. Okay, I can upload the answer in Webble, just that without any solution. Okay, I can upload the answers in Webble without any solution for the calculation. For the calculation, obviously. Okay. Okay, now all of you have signed the attendance.